Hi. So it is 11 o'clock now, and the session is acting alive. Well, seems that we're having problem reaching out Dr. Shalom. Maybe I will just hand over to Tim to start, and I will try to. No, no, Scott, you have put up the wrong one. Okay, okay. Let's just hand over to Tim, and I will reaching out another speaker in the backstage. And here we go, Tim.
Okay, you can hear me?
Yes, we can hear you perfectly. We can hear you perfectly.
Okay. All right. Well, my name is Tim Edwards, and I'm Senior Vice President of Analog and Platform at efabless Incorporated, the online platform for chip design and fabrication and more using open source tools, and host for a community of designers and service providing partners. I may be joined by Mohammed Shalan, Associate Professor in the Computer Science and Engineering Department at the American University in Cairo. The task of designing a chip has always been considered a specialized domain of electrical engineering, so much so that it's hard to find companies that don't have separate groups, or at least different people, doing design, layout, and verification. The state of hardware design is sort of like what it would be like if software developers had to program in assembly or even machine code. Or maybe a better comparison is that if after writing a program, you had to hand it off to somebody else to compile it, and then they had to hand it off to somebody else to check that the program worked. Everybody in the software world knows that the scope of software increased dramatically with the introduction of high-level languages and compilers. And it increased dramatically again with the availability of open source operating systems. And it's increasing again now with the availability of huge public repositories, collaborative development, and continuous integration. There's a parallel in the hardware world to each of these productivity gains in the software world, which I'll discuss in just a minute. The fact that these things have been slow to catch on in the hardware world is mostly due to a combination of mindset and corporate influences. For the mindset part, there's certainly a view that hardware design requires specialized knowledge of the kind that can only be obtained by getting an advanced degree in electrical engineering, preferably from a major world-renowned research university. There's also, I think, a mental block around the cycle time for full custom hardware, since no technological advances are going to bring down the time to manufacture by orders of magnitude. In fact, the opposite is true, that the more modern fabrication technologies keep adding more layers and complexity to the manufacturing process. The main gains in manufacturing time have come from streamlining the process, but as you know, practices like just-in-time delivery have not fared well during the pandemic, and their continued use is questionable now that people understand how fragile some of the supply chains are. Finally, there's the issue of manufacturing costs, since production mask sets are prohibitively expensive for someone who just wants to play around with an idea. So to counter the problem of expense, working with multi-project wafer runs, or shuttle runs as they're called, is a must. Whether a shuttle run is available and how often depends on the foundry, and some foundries are just not interested in the overhead of handling many customers and many different project layouts over a short period of time and repetitively. Also, working with older, more mature processes is a way to keep costs down. And while the cycle time of a custom chip design can't be brought down due to essentially nothing, like for software development projects, the cycle time isn't that much different than it is for working with any board level design. It's just necessary to set expectations around the quarter to half year delay involved between submitting a design and getting back a working part. As for the expectation that chip design requires a PhD level knowledge and experience, it's really just a matter of having experienced people create a set of building blocks and a set of tools for assembling those building blocks. Generally speaking, it can be that simple. It's not trivially simple, but as long as the building blocks work as advertised, then the problem is mostly one of interfacing. And software developers know a lot about interfacing between one software package and another. In chip design, there are additional considerations like managing voltage domains, current density limits, ESD protection, power dissipation. but many of those can be handled automatically, even if that requires overly conservative design practices. The primary issue in making custom chip design as accessible as software development is really none of the aforementioned things. It's mostly a lack of clearly documented examples and instructions. And the lack of examples and instructions is due to the traditionally highly proprietary nature of foundry processes and the corresponding commercial design tools. At efabless, we've always championed the use of open source tools for chip design. And since I'm also the developer of open source electronic design automation tools myself, I've been maintaining and developing my own set of tools on the system while championing the use of open source tools generally and encouraging developers everywhere to keep providing more and better tools for the job. The problem with the use of open source tools for making chips is that unlike open source software for most everything else, open source tools for chip design rely entirely on that traditionally proprietary foundry data to run. Every tool has to access a process design kit, or PDK, which describes a specific foundry process in terms of device characteristics, rules of design related to that process, and ready-made libraries of components, both digital and analog. In the past, at efabless, we've tried to find some useful balance between open source tools and proprietary foundry data. Ultimately, much of the information users need to work with has to be kept from the general public. This makes the software tool development very slow and inefficient, discourages collaboration on software projects, and makes collaboration on hardware projects all but impossible. But now, there's the Google SkyWater project. The Google SkyWater open source PDK was launched about a year ago with the repository on GitHub under Google/SkyWater-PDK. This is a complete set of open source, publicly accessible data and files describing the SkyWater 130 nanometer CMOS process. To relate that back to what I've just been talking about, it's an older process node, one which was considered cutting edge more than 20 years ago. But that means that it's relatively cheap to create mask sets for this process and relatively cheap to manufacture the wafers. The device characteristics in the form of simulatable SPICE models are all available. There are libraries of components, mainly for primitive devices, digital standard cells with characterized timing, and cells for building out a pad frame, and also SRAM bit cells. It's a somewhat weak offering, especially with regard to more complex analog or mixed signal circuits, but it's enough to design a complete chip with, whether that chip is going to be digital, analog, or mixed signal. So to summarize what all of this means, we now have a fully described foundry process that's been posted online, and anyone can download it and design something with it. But the initial offering looks like a giant unorganized data dump, and good luck to anyone who wants to take that and design a chip with it. So where efabless comes into this is that we're trying to find a way to make this open source PDK useful for people who want to design chips, both people who have designed chips before, either academically or professionally, and also people who have never designed a chip before. The first part of that effort involves organizing the data dump, especially for use with open source tools. Google is responsible for some of that organization, and efabless aims to make the PDK work well with specific open source design tools and to describe and demonstrate viable design flows using those tools. The original PDK from SkyWater was designed to be used with a couple of well-known proprietary electronic design automation software tools, but was so tied into that ecosystem that it was actually a lot of effort to pull all the standard formats like SPICE, LEF, Liberty, GDS, and Verilog, and then collect them in a form where open source tools could find them and make use of them. The second part of that involves collaborating with a number of tool developers to deliver the tools, methods, and circuits needed by designers. A few examples of these collaborations includes the OpenRAM project from the University of California at Santa Cruz to create an SRAM compiler using the bit cell layouts available in the library. That project has already delivered a set of macros from 1 to 4 kilobytes of SRAM arrays that have been put in a repository and used in projects. More macros are on the way, and eventually users will be able to make their own custom SRAM blocks. OpenLane is a digital synthesis, placement, and routing tool based on the OpenRoad project tools. OpenLane achieves what is close to a one-button push deliverable of a digital circuit layout from a high-level description language. And I'll have Mohammed Shalan, the principal developer of OpenLane, describe the design flow using it as part of this presentation a little later on. The RISC-V project from Berkeley, which is now its own foundation, has really brought microprocessor design to the masses with an open source instruction set. The very simple and straightforward open source implementation of the Pico RV32 microcontroller by Claire Wolf isn't necessarily the best choice for custom chip hardware, but it is so well documented and easy to understand that it forms a natural backbone to any chip design project needing software control and communication with the outside world. The third part of the effort involves creating a community of people around the PDK, the tools, and the design flows. We recognize that a good PDK is an effort by many people. Generating reference designs and valuable circuits requires the input of numerous specialists. Because the PDK is open source, this is really the first time that an entire public online community could be built around an actual foundry process and share experiences, problems, solutions, and then share actual circuit design, simulations, and layout. This community exists mostly in a Slack workspace and has been growing quickly for over a year now, with 1,776 members the last time I checked. The fourth part of that effort is to make the process available for people to submit chip designs to SkyWater and to get them manufactured. Google is underwriting part of that effort to provide a number of free shuttle runs to anyone who wants to design a chip using the open source flow and to make their designs publicly available on a Git repository for other people to use, remix, or enhance. efabless is managing the part of collecting the user projects, running checks for manufacturability, preparing all the data for tape out, and delivering the finished product back to the designer. We're also providing a series of shuttle runs called Chip Ignite for a fee comparable to other shuttle services with terms that are less restrictive than the free shuttle runs underwritten by Google. So let me put all of this together. We have an open source PDK. We have open source descriptions of microcontrollers using an open source instruction set. We have the synthesis, place, and route tools for turning the circuit descriptions into actual layout. We have SRAM blocks. We have cells for building a pad frame. We have a community to lean on for help and advice. And we have a shuttle run service for handling chip submission, manufacture, and delivery. So it looks like we have everything we need to build a chip. But we want to do much more than that. We want to let anybody who wants to build a chip without having to be an expert in VLSI technology and device physics. So here's how we're doing it. Our first task was to make a reference design on the SkyWater process, which we did about a year and a half ago. At efabless, we'd already gone through this process with a closed source foundry process and various closed source blocks, such as the SRAM and analog IP. It was really only necessary to replace all of the closed source blocks with open source ones. We used the same Pico RV32 microcontroller core and reused some of the digital peripheral blocks we had designed for it, such as SPI and I2C interfaces and a counter timer module. We redesigned all of the peripheral blocks around a wishbone bus, which made the design much more modular and easier to add additional components to. We used an Open RAM macro for the memory, as well as a flip-flop based RAM array. Mostly that was to keep the probability of success higher by having some fail-safes against circuits that might end up with issues on the first fabrication attempt. We called this reference design Strive, taped it out about a year and a half ago, mostly as a way to understand the process and the tools. It was more of a proof of concept than anything particularly useful. We then moved on to designing the Caravel harness chip. If you're wondering about what the harness means, it means that the chip is designed to be a wrapper around a user project. As I said earlier, making chip design feasible for an end user not familiar with all the details of a foundry process means that many of the tasks common to getting the chip designed and taped out need to be either automated or pre-designed. The harness around the user project is all pre-designed. It contains the components that we put into the Strive proof of concept chip, which is to say a RISC-V processor core with some internal SRAM memory and various interfaces to the outside world, including an SPI flash memory controller, UART, an SPI and I2C controllers, and a large bank of general purpose digital input and output. The pad frame of the chip was pre-designed using a pad cell library from SkyWater. The power domains were also pre-planned and ESD was taken care of. So this is the layout of the chip. We try to compress the processor and interfaces into the bottom area of the chip and leave as much room as we can at the top for user projects. By keeping the amount of onboard SRAM small, we leave over 10 square millimeters of area for use by the end user for a project. The most important constraint of the harness was to define a size of the chip that would allow a reasonable number to fit on one reticle without giving up too much space. Standardization is the key here. The more that every project on the wafer looks the same, the easier it is to handle dicing, packaging, and distribution. The larger the total chip size, the fewer projects we would be able to accommodate per shuttle run. So we settled on an approximately 3.5 millimeter by 5 millimeter chip size. Subtracting out the processor and the pad frame, that leaves a space of about 3 millimeters by 3.5 millimeters area for the user projects, or just over 10 square millimeters. That size of chips allows us to put 40 projects in one wafer reticle in a regular 6x7 array with 2 of the spaces reserved for use by the foundry for test structures. The reticle size is a little over 25 millimeters by 31 millimeters. This yields up to 1,280 chips per wafer, but the key figure there is the number 40, which is the total number of different projects that can be manufactured on a single shuttle run. Another important constraint of the harness was to define the pinout and the placement of pins, and to keep that configuration for all future shuttle runs. That allows us to keep the packaging consistent between shuttle runs, which keeps the cost down. Our ideal packaging setup is to use a third-party vendor to post-process the wafer and add WLCSP bump bonds to the front side of the wafer. With a consistent package footprint for all projects, we can define a demonstration board to be used with the completed project. The goal here was to further reduce the cost of manufacturing and assembling the demonstration board by making sure that the bump bonds were large enough and with enough spacing between them to run a printed circuit board trace between the solder bumps, given a standard minimum design rule for simple and cheap 2-layer circuit boards. Given that configuration, we were able to generate a reference board design that can route all the pin connections out on one side of a board without resorting to the more expensive options like a 4-layer board or blind vias. The constraint of being able to route all of the internal bump bonds out was what determined the total number of pins on the chip, which came to a 6x10 array or 60 pins. Now, obviously not every project can make do with only 60 pins. So the configuration of the harness chip involves a second trade-off. By having a complete microprocessor attached to the user area, the microcontroller can be used to access many internal signals of the user project. Now, running input and output through the microcontroller is less flexible, but assuming that most projects will have some static or low-speed signaling, those parts can be attached internally to the microcontroller, and the remainder allocated to the chip pins, which greatly increases the overall amount of input-output that can be used with the user project. Our final set of pins for the Caravel harness chip came to 38 general-purpose I/O to be used by the user project, 8 I/O pins needed by and reserved exclusively for the onboard microcontroller, and 14 power and ground pins comprising several independent power domains, including both 3.3 to 5 volt domains and the core 1.8 volt digital domain. The harness chip design adds a so-called logic analyzer to the list of digital peripherals connected to the microcontroller's wishbone bus. The logic analyzer has 128 bits of full duplex digital signaling. As the name implies, a standard use case is to use a circuit for monitoring signals in the user project. But it can also be used for any input-output into and out of the user project area, both for control and for monitoring, so it's much more general purpose than just a logic analyzer. Its main limitation as a logic analyzer is the onboard SRAM, because while it can sample data at a rate of maybe 30 megahertz or so, it won't be able to get the information off-chip at that rate, so it would have to be buffered in memory, and that limits the sample length that can be captured. The 38 general-purpose I/O pins are the main connection between the user area and the outside world. Every pad is multiplexed between the user area and the microcontroller. Every pad is exceedingly complex, too, so we had worked hard to make every pad look as simple as possible to the end user. That means that the user project area sees each pad as a simple bidirectional digital pad with input, and output enable. Other aspects of pad behavior are static settings. There are about a dozen such control signals for each pad. Since there are 38 GPIO pads available to the user project, to prevent the need to have 38 times 12 signals and wires running around the perimeter of the chip, I opted to create a serial register wrapping around the pad frame. All of the static signals that configure how the pad operates are serially loaded on command. In addition to the basic pad configuration, there's also a control signal that determines whether the pad is under the control of the user area or under control of the microcontroller. When pins are under the control of the processor, a number of pins have specific functions for use by the processor, such as additional SPI interfaces, an I2C interface, a UART, external interrupt, and monitoring of select internal signals. The user project designer can opt to let the pins be used by the processor or leverage them for the user project. Additional features available on the microcontroller to help with communication between the processor and the user project include interrupts, counter timers, programmable clocks, and a pass-through SPI flash programming. The resources that complete the operation of the full chip include a power-on reset circuit and a digital locked loop clock controller. The power-on reset is the first analog component created specifically for the Caravel chip. It monitors the power supply and will generate a reset until the power supply reaches a good value and is stable with an approximately 15 millisecond delay. The digital locked loop synchronizes an external clock to an onboard ring oscillator to provide an onboard clock with about a factor of 2 range from about 75 megahertz to 150 megahertz. The processor can also bypass the digital locked loop and run directly off of the clock pin input, which would have a maximum rate of about 60 megahertz. So that's a pretty thorough description of the hardware resources of the Caravel harness chip. The second aspect of the Caravel chip is the user projects and how the users build them. To make sure that the design process is streamlined, the user project designer doesn't and can't modify the design of the surrounding Caravel harness chip. This is necessarily restrictive since it helps to make the whole chip assembly and preparation for tape-out much easier to automate. The user just needs to fill in the area in the middle. The user project area is contained in the harness chip's design files as an empty wrapper. It's not completely empty since it has all of the pins that the user area can connect to, including the GPIO control and data lines and the whole logic analyzer interface, and the extra clocks, reset, and interrupt signals. For the power supply connections, we do make one concession to the operation of the place and route tools by having a set of pre-placed power and ground rings and at the perimeter of the user project area. The place and route tools are expected to see this power ring and connect to it as needed. The user area is considered to be inside the area of those power rings, although the place and route tools can connect to the power rings outside of the user area boundary. Everything else outside of the user area boundaries is off limits to the designer. The designer just needs to have access to the various wrapper files, such as a Verilog module and layout with pin names and placements, all of which is available from a public Git repository. The contents of the repository include a makefile with various targets that allow the designer to connect their project into the Caravel harness chip, and they're connected into the framework and prepare it for submission to a shuttle run. All of this is described in the documentation that can be found on the user project repository webpage. The main job of the designer is to figure out what it is that they want to implement in custom hardware and whether or not it will fit in 10 square millimeters, what resources from the PDK they will need, and how they want to make use of the Caravel harness chip resources. We have the capability for analog and mixed signal design flows, but since the point of this talk is to argue for custom chip design as an essentially software development process, today we'll concentrate on describing the digital synthesis flow, which can be done with little understanding of the underlying process and devices. Mohammed Shalan will describe the design flow through the synthesis, placement, and routing using OpenLane. Mohammed?
Yeah, we're having Dr. Shalan on the webcam feed, and we're now switching the slides. And Dr. Shalan, your screen is on the broadcast. Yeah, thank you.
Yeah, thanks, Tim. Hello, everyone. OpenLane is open source ASIC physical implementation flow. that can produce clean and ready to fabricate layouts from hardware description at treasure transfer level, or RTL in short. This is like kind of a data flow abstraction when it comes to scrapping hardware. OpenLens development started as a part of an experiment to implement 100% open source system chips, or SoCs. In this experiment, we taped out a family of SoCs. We called them Strive. We used only open source EDA tools, thanks to Open Road uses and Kubeflow projects, open source RTL, and eventually, if you mine the internet, you'll find like hundreds of open source RTL ready to be used. One of these IPs or RTL designs that we use is PQRV, as Tim mentioned, which also used by Caravel and Caravan. Also, we use the open source PDK, the SkyWater PDK. Moreover, the development for such an experiment basically was done using Linux environments. But what's Flow? Flow is a set of scripts and utilities to automate the execution of different CAD tools to carry out the implementation process. We usually use the term electronics design automation, or in short, EDA, to refer to the CAD tools used for designing electronics. But why Flow? Well, Asic design is a complex process that involves tens of steps. Not only that, only trained EE designers with deep knowledge of semiconductor physics, surface design, and automation algorithm will be able to utilize such EDA tools to implement an ASIC. To understand how complex ASIC development is, let's compare it to software development process. So this is a typical software development process, where basically that starts with requirements gathering and analysis, followed by design activities, implementation, testing, and finally deployment. Software implementation involves coding and compilation, which is a push-button process, and it's automated using a compiler, which automatically translates the source code into machine code into executable image. In hardware or in ASIC design, basically this is very similar to software, as you can see. So there are lots of similarities, and actually these similarities are due to the fact that when it comes to designing ASIC, we wanted to accelerate the product to the market. So eventually relied on mature software engineering practices to increase the productivity, thus reduce time to market. So they look very similar, as you can see, except of like a few differences. For example, we have a chip fabrication, because eventually the team that implements or designs the ASIC is not the one that fabricates it. Eventually, there is the design team or the ASIC development team produces some output, which eventually will be sent out for fabrication. Also, there are lots of testing, verification, and validations, which basically similar to what we do in software, but they are a little bit different. I'm going to explain them shortly. Also, there is no deployment, because eventually, typically, a chip is not the final product. A chip will be used to build like a system. So the system is basically the one that's being deployed. So let's go over the other differences that I mentioned. So fabrication is a process of realizing the design into silicon. It's a complex, expensive process that involves hundreds of steps. During fabrication, a chip will be built one layer at a time. And for each layer, a pattern is burned into light-sensitive material covering the silicon wafer by applying light with a specific wavelength through masks. This followed by development steps. The burning part is called photolithography, and as an ASIC engineer, you are responsible for creating the layout of the mask sets, which basically will be used in photolithography. Testing is critical in software. Testing makes sure that the requirements are implemented completely and correctly. Because of its importance, most of the software development time is spent in testing. In ASIC development, it's even more critical. Having a faulty or non-functional chip means the loss of huge amount of money and effort. Moreover, ASIC development doesn't have the luxury of fixing bugs after deployment, which is a common practice in software. In ASIC, software testing is equivalent to several activities done before and after chip fabrication to ensure that the chip will be or is functional. This includes several verification steps during the development process, and this is typically done either through simulation or formal methods. And after fabrication, we test the chips against manufacturing defects. So when we say testing in the context of ASIC design, really we refer to testing the chip after fabrication against the manufacturing defects, because the manufacturing process is not perfect, and so it doesn't result in 100% yield or functional chips. Eventually, a small percentage of the chips basically will be faulty because of the limitation of the manufacturing process. Also, we perform validation, which eventually is make sure that the functionality that we implemented into chip eventually is okay, or eventually they are fine. By testing the chip, basically in the lab environment, by building applications around the chip and basically testing different functions according to the requirements that are started with. So RTL to layer transformation involves lots of tools, actually too many tools. And eventually to do ASIC design, as designer, you need basically to be aware of all of these tools and how they function. And not only that, you need also to be aware of what you are building, because as you will see, you are responsible basically for defining constraints, and sometimes you might need to update your design eventually to address some issues. Also, as designer, you need to be aware of how chips function and how they are fabricated, as well as the algorithm used by the EDA tools. And typically, a large, diverse team basically will work on the development of a chip. So to understand the ASIC implementation process, let's have a closer yet simplified look at the RTL to layout transformation process. And this basically will let us understand and appreciate why we need a flow. The process starts with the verified RTL, and it involves synthesis, floor planning, part planning, placement, clock tree synthesis, routing, and sign-off steps. Eventually, I'm not listing everything here. I'm just listing the most important steps. There are other steps that are not mentioned here, but they are equally important and they are essential as well. So, and the end product of this process is the the layouts of the masks, typically in the format called GDS2. The transformation requires information and data provided the PDK. So, starting with the synthesis. So, in synthesis, we transfer the hardware description, which typically at the RTL level, into a circuit. This circuit is made out of components from a library of pre-designed, ready-to-use components that we refer to them as cells. The end result of the synthesis is the gate level netlist, which is also described using hardware description languages such as Verilog or VHDL. Because any HDL allows that the description of the hardware in different abstraction levels. So the gate level netlist is just structure this description of the hardware by showing the component and how they are interconnected together. Verification activities using simulations and formal methods are also performed here in order to ensure that the translation is error-free. So using simulation and formal methods, we ensure that the gate level netlist performs basically the same function as the RTL that we started with. Typically, the synthesis process is guided by constraints provided by the design. These constraints could include stuff like the target clock frequency. The library, which is needed for synthesis, is made of the building block. As I mentioned, these building blocks are called cells, and these cells eventually they have regular shapes. So their layouts that are pre-designed eventually are enclosed by rectangles, and these rectangles eventually they do have fixed heights, and the width eventually is discrete. So they look like Lego blocks. So they are simple, regular, yet powerful enough to build almost anything. And eventually, the regular layout of these standard cells simplifies the layout generation automation process that basically we're going to cover shortly. Each one of these building blocks or cells in the library comes with different models. We call them views, and these views utilized by different EDA tools during the process. After synthesis comes floor and power planning. The objective here is to plan the silicon area and create robust power distribution network to power the chip. Floor planning means different things based whether you are implementing a single component in your chip or the whole chip. So, for example, in Caravel, floor planning is basically how to partition the available silicon area between user space, management area, storage area. But when it comes to the user's area, eventually this can be considered as one building block in the chip, which typically referred to as a macro. So floor planning, basically the whole chip or a macro, eventually they're a little bit different. So in chip floor planning, as I mentioned, we partition the silicon between different building blocks. When it comes to a macro, eventually it's different because in macro, just one building block in the chip. So what we do, we just define the area that will include the circuit that implements this macro. This area typically has a rectangular shape or sometimes rectilinear shapes as well. Also, in this step, we define where are the input and outputs of the pins, and typically they are placed on the edges. Also, in this step, we prepare this area enclosed by this rectangle, basically for the following steps, and the main two steps after floor planning, eventually placement and routing. So placement eventually requires rows to be used by the placement tool to place the cells. And for that, virtual rows basically will be created. Also, something called routing tracks will be created based on the PDK data in order also to help the router later basically to carry out the routing process. In power planning, the power distribution network, or in short PDN, is constructed. Typically, the chip is powered by multiple VDD and ground pins. And the power pins are connected to all the components through typical rings and vertical and horizontal metal straps. The rings and metal straps are all made of wide, thick wires in order to reduce their resistance. And this is something essential because eventually we need to deliver the supply voltage as it is without basically, so we need to eliminate any voltage drop that could happen on the power distribution network. That's why we reduce the resistance. Also, we make them basically wide and thick enough to address problems such as the electromigration, when basically we have high currents demanded by the cells during operations. After floor planning and power planning comes the placement. For macros, we place the gate level netlist on the virtual rows created during the macro floor planning. It's obvious that connected cells should be placed closer to each other to enable successful routing and to reduce the interconnect delay, because the wire delay is proportional to its length. Typically, cell placement is done in two steps: global placement followed by detailed placement. In global placement, we try to find the optimal position or location for every one of the cells in the gate level net list. These positions are not necessarily legal, which means cells, as you can see, can be off rows and also may overlap as well. So that's why global placement typically followed by detailed placement, where the cells basically are moved slightly around their optimal positions in order to legalize their locations. So after detailed placement, they will be aligned. They are placed on rows, and no overlaps basically will be there. And also they will be aligned to vertical lines that refer to them basically created by sites. After placement comes routing, but before performing routing, we need to eventually to route an important signal, which is the clock. And we refer to this step as the clock tree synthesis, because eventually in this step, we create clock distribution network to deliver the clock to all clock cells, such as the flip-flops. So we construct a clock distribution network, and this clock distribution network typically in the form of tree made out of inverters and buffers from the standard cell library. And eventually, this tree will deliver the clock to all the cells that are clocked like flip-flops and latches. And the objective here is to deliver the clock in a good shape with minimum skew and minimum latency. And clock latency means the arrival of clock signal at the flip-flops at different point of time. So we want basically the clock edge to arrive at all clocked elements at almost at the same time. This is hard to achieve, but we'll try eventually to minimize the skew if we cannot just eliminate all the skews. When we do perform clock tree synthesis to create the clock distribution network, typically we use well-known structures such as X tree and H tree. After clock tree synthesis comes the routing, and routing eventually we have the placement of the cells, and we have fixed number of routing layers based on the fabrication process. For example, in the SKY130 process, we have 6 routing layers. These 6 routing layers, they are named LI, which stands for local interconnect, followed by 5 metal layers, metal 1 up to metal 5. Eventually, the PTK contains data about the characteristics or the properties of these routing layers. And as Tim mentioned, eventually, this is the metal stack. And for every layer, we have basically information related to the preferred routing direction, because typically when we create wires on a routing layer, basically the wires in each layer basically will be in either horizontal or vertical. So this was referred to as preferred routing direction. Also specifies the minimum spacing, minimum width, etc. Also, the PDK defines what are the available vias to be used, and the via is a vertical structure which can be used to connect 2 wire segments on 2 different routing layers together. Most routers are grid-based, and the grid is constructed for every routing layer, use the data provided by PDK, and the algorithm used to perform the routing are similar to those used to find the shortest path between 2 points in a maze. So most of the routing algorithm, actually we refer to them basically as maze routing algorithms. As the routing grid is vast, a divide and conquer approach is used for routing. First, global routing is performed using low-resolution grid to generate what we refer to as routing guides. And then these routing guides will be used by the next step, which is the detailed routing, to use a fine-grained grids to implement the actual wiring. Once done with the routing, we can construct the final layout, which undergoes a set of verification activities that include design rule checking to ensure that rules set by the fab are satisfied, layout versus schematic, or in short LVS, to ensure that the final layout matches the RTL that we started with, static timing analysis, or STA, to ensure that the implementation doesn't have any timing violations and the chip will run successfully at the desired clock frequency. Once passed, the layout is kind of ready for fabrication. We call this milestone the tape out, which actually a term that was coined in 1970s, because historically engineers use magnetic tapes to store all the Asic design files, and the event of carrying out the tape to the foundry was thus called tape out. Throughout the implementation process that I briefly described, we have several file formats used basically to pass data information between different tools implementing different steps. Here I'm listing some of them. So the Liberty format, which text format, contains electrical models like timing models, power models, etc. for standard cells in the library and also for the finished design. SDS, or synopsis design constraint, this is to capture the timing and design constraint, also text file. Library exchange format, or LEF, it has an abstract layout for the cells, also abstract layout for the finished design, as well as contains technology information in a special version of the LEF file called the technology LEF. Design exchange format, or DEF, encapsulates the design data basically during the ASIC implementation process. So when you do floor planning, the end result eventually will be basically in the form of the file, which will be passed to the placer, that eventually will add the placement information to the same diff file, and then when you do routing, the routing information will be added to the same diff file. This diff file eventually can be used to generate the final layout when we are done, by replacing the abstract representation of the cells inside basically the file by their equivalent GDS, which stands for the graphic design system format, that basically encapsulates all the layout details of the cells. Now, after outlining the ASIC development process, it's obvious that automation is complex yet essential. Typically, we develop a collection of scripts and utilities to automate this process, and this is what I mentioned earlier and called ASIC flow. Building an open source ASIC flow is tricky because of the usage of open source ADA tools. So while building OpenLane, we paid lots of attention to tools qualifications, tools calibration, and also we have to take care of any missing tools. For OpenLane, we set the goals for OpenLane as a flow to produce a clean layout without any human intervention. As Tim mentioned, we try basically to make it basically as a single push button flow as possible. And this is basically to make it very easy to everyone to use. And this is basically done through abstraction, automation, and machine intelligence. In short, we designed and implemented OpenLane to be used by anyone and everyone, even without any EE background. So to start working with OpenLane, you just need to have Docker installed on your machine. If you want to run natively, you may consult the documentation for containerless operation. So all you need to do is just clone the repo and then basically call certain make targets to build OpenLane and then to build the PDK. Once this is done, you can use another make target to start the container and to mount some local folders basically inside the containers for your files and the results. And eventually, if you want to try out the flow comes with large number of designs, and these designs eventually can help you to understand what's going on. And for us, we use these designs as well for continuous integration regression testing. So one of the provided designs is the XT, which is hardware implementation for the XT cipher. So to run or to convert the RTL of this to basically to hard macro, all you need to do is just type this command. And eventually, after a few minutes, the flow will finish with a clean GDS2 for the cipher. And eventually, as a result of this execution, you will end up basically with folder structure basically similar to this one, where basically different subfolders basically contains information and data generated by different steps. Eventually, for this particular design, when it finishes, eventually you will get reports, and the report basically will show that this design has about 3K cells, and the macro has 262 input-output pins, and it occupies the area of 375 by 386 squared microns. And the final layout in the GDS2 format eventually will be under results/magic folder. The operation of OpenLane is controlled by configuration parameters, and these configuration parameters eventually will be provided for the design, basically in the config.tcl file, which basically should reside under the folder that contains the RTL files. Also, we have other configurations that are technology specific and flow specific. So typically as a designer, you need to focus only on the design parameters in the config.tcl file to specify stuff like what are the RTL files, the clock period, the constraints, utilizations, and plus other parameters, all of them documented. And eventually, if you have doubts, what are basically the good parameters or the good values for some of these parameters, like what's basically the best code utilization to use, or the clock period, eventually OpenLane has some utility that can sweep the parameters to find the best combination of values for these parameters to produce clean layouts. Here I'm showing basically the layout results, basically executing the XT using the OpenLane flow. So this is the layout after flow planning, and as you can see, the virtual rows, the power straps, and the pins. This is after global placement, where you can see the cells are placed but not on rows, so they are off rows. And eventually, after doing the till placement, their placements will be legalized. This is after doing the till routing, and as you can see now, the cells are hidden beneath basically the forest of routes. So all of these, what we are seeing here, eventually these are the wires created by the routers to implement the interconnect between these cells. And finally, this is the final GDS after replacing the abstract views of the cells by the detailed GDS layout, and basically to generate the final GDS2. Finally, I would like to invite you to try out and contribute to OpenLane. So here are some pointers. Thank you. Back to you, Tim.
Yeah, thank you. We're having around 10 minutes left, so I'm so sorry that. Anyway, thank you, Tim.
Yeah, I'll try to run quickly through the last part of this in the interest of time. But of course, once you have designed something under OpenLane, you have your layout. But then if you were a software designer designing something for, say, a FPGA, you'd expect to be targeting some system that's on a development board and have all the resources you need to connect to a computer, download your configuration. And so we want to provide that same sort of environment. So we have a development board, And it's designed so that you can create your, have your chip and download whatever you have designed for your verification, download that software to that development board. And so the power up sequence for every project, your development board will power up the microcontroller. The power on reset circuit will enable the microcontroller, then the microcontroller will run your program from an SPI flash. The program then enables the user area power supply. The program waits for the user area power supply to go valid. The program configures the GPIO for the user project. And then the program optionally resets the user project and can control or monitor that user project. So all of this can be done and should be done with Verilog simulation as part of your design. Even designs that are analog in nature should be represented by some behavioral model and run through simulation. So the designer is responsible for ensuring the functional correctness of the design by gate level simulation, layout versus schematic, layout versus Verilog. A lot of that is done through OpenLane, as Mohammed Shalan was mentioning. When it goes to efabless for fabrication, we have scripts that run a basic pre-check to ensure manufacturability. That mainly runs DRC checks, but there are also checks on repository metadata, such as open source license headers, a valid README file that helps to make sure that open source projects can be seen and used by other people. The pre-check also runs an XOR check, which makes sure that your user project is defined within the area that is allocated to it and properly connects to the rest of the harness chip around it. So we've worked to make the submission process straightforward, well documented, and easy to follow by example. So the efabless website has a link to each shuttle run, and from there is a full set of links to the repositories for the Caravel chip, the user project wrapper, the open source process PDK, and the open source EDA tools such as OpenLane. The submission process uses efabless's platforms where the designer can create a project on the platform, and that gets populated by cloning the designer's project from a Git repository. After that, the designer just needs to follow the steps outlined on the web page and declare the project to be a submission for the shuttle run. The project is then queued on the system. The user project layout is integrated into the Caravel harness. Finishing touches like seal ring and fill density pattern are added. And the completed chip is passed through the same pre-check process that the user has completed for the project layout. If it passes the final pre-check, then it's ready to go to manufacture, and the designer just needs to wait for the part to arrive in the mail. So once you get back your development board with the project on it, assuming you've run simulations from the Caravel chip from the top level and you've verified the chip operation, you should be able to simply plug in the board into the host computer, and you should have a valid hex program you can download to the SPI flash and run the program and get running. So the project design process, submission process, and shuttle runs I've been describing have been available now for a bit over a year and a half. Well, about a half a year. And we've done just 3 shuttle runs, and the submission window for 2 of those just closed last month. The first shuttle run is almost done being manufactured, so I don't have anything to show to you from completed projects, but there are a number of projects that I can provide examples of here. Just to quickly go through them, we have open FPGA cores, RISC-V cores, crypto miners, time-to-digital converters, RISC-V floating point processors, CAN bus controllers, and so forth. So I'd like to conclude by stressing that the Caravel harness chip is a fluid concept and a continual work in progress. Because the user designs on the shuttle runs are open source, once a design gets validated through measurement, it can be put back into the Caravel harness design to make a future version of the Caravel chip better. For example, once we have circuits for LDO voltage regulators, then we'll no longer need those as board level components. And that can, once we have ADCs and DACs, we can enhance that, logic analyzer, and it would be more like a full onboard oscilloscope. So it should be clear that we're only limited by the community's willingness to be involved and actively helping the Caravel harness to be a better platform. And given the enthusiasm I've seen, that's not any limitation. efabless, Google, and SkyWater have brought open source to hardware, and we see it as a game changer. Full custom hardware has never been easier for the professional, the student, or the hobbyist. If you know software, then you can make your own chip. Come join in on the fun, and thank you for listening.
Thank you. And we buy some time from the board of COSCUP, so we're still having the Q&A session, but we need to do it very quick. So here's the question list, and maybe you can just go go for yourself, and I will scroll the screen for you. So this the first one is how mature is the open LAN? Could a layman who knows how to write Verilog to use it without any too many hiccups?
Well, it's pretty mature in the sense that we use it first to tape out the Strive family of SoCs, and then OpenLane was used by like more than 100 designs for the first OpenMPW and the second OpenMPW runs. And I can tell you that many designs were submitted by individuals who are not ASIC designers. Maybe they had some knowledge about Verilog and FPGA. Maybe they did some FPGA experimentation in the past, but they never did ASIC before. And eventually, we have several of these those individuals who submitted designs and done the designs using OpenLane.
I see. And the next question is that, is there any chance that we can have Vex RISC-V in Caravel? Oh, so this one is mentioning a popular RISC-V implementation that's called Vex RISC-V, which could put Linux on it. But I'm wondering, which one should be? I don't know.
Yeah, the answer is that if you're looking for something that you would be able to put Linux on, probably not. Just given the fact that this is a 130 nanometer process and you've got 10 millimeter squared of space, you can do small microcontrollers. Doing something that would support an entire operating system like Linux, probably not.
I see. Okay, so we'll jump to the next question. Is it okay to provide some links that point to the mixed signal part that you skipped?
Yeah, there were links to the efabless site. So go to the efabless site. That will get you, probably the best resource is the Slack channel that I referred to, and I think I had a link to that as well. Yeah, join.skywater.tool. So if you go to that, there's a channel, Analog Design, that is a lot of discussion about doing the analog and mixed signal circuit designs.
Okay. Hope this is the last one. Nope, it's still not the last one. Is the caliber in the OpenLane or is it missing? I'm not quite sure what he's referring to.
Okay, we have open source tools that basically performing the job of Caliber. Caliber is a commercial EDA tool which is used for several things like extraction, LVS, design rule checking, ERC, etc. So we have open source tools that perform the function or the functions that can be performed by Caliber. However, it's known that Caliber basically is the standard sign-off tools by fabs. So eventually, the fab will run Caliber at its sites before fabrication. But we for us, we don't use Caliber because Caliber is not an open source tool, and all of our work eventually is based on open source tools.
I see. Okay. Is there any plan on applying those two on ASIC development toward automotive market? Because some functional safety aspects should be considered as well. So, okay.
Yeah, automotive, medical, military, all of those, they have very stringent requirements. We have interest from all of those sectors. So it's really a matter of how those sectors really will deal with the stability of the tools and trust. It's really a trust of the tools issue more than anything else.
Okay, so we have a appreciate from the audience. If it's not a question, but he really want to address the thank of the talk, and we're and that's all we have. And thank you all. The next session will be in 1 minute, so I need to pull everyone off from this session and bring up the next speaker. So thank you all, thank you Ting, and thank you Dr. Mohammed Shalom, and goodbye. Thank you.
All right, thank you.
Thank you.
Take care. Bye-bye.
Bye-bye.